Hi, this is Big Tuition, and this is a quick review of the chapter of permutation and combination along with some probability. Permutation and combination are basically counting ways for things to happen or for objects to be arranged. Knowing how these things can happen can give us a probability, a sense of the probability of the chance of things happening. So for example, if we want to, let's say there are 10 ways of things happening and out of which 3 ways are desirable. So then the chance of a desirable outcome happening is actually 3 out of 10, assuming each way has the same probability of happening. Before jumping deeper into what exactly permutation and combination are about, it's important to understand the concept of independent and mutually exclusive events. Independent events or occurrences are events that do not affect each other. For example, if I flip a coin right now and I roll a dice, the probability should be independent between the two. So no matter whether if I flip a coin before or after I roll the dice, it should still be 50% heads, 50% tails. Whereas if I roll a dice, no matter what happened, it will be 1/6. 1/6 chance of getting a 2, 1/6 chance of getting a 3, so on and so forth. However, an example of a non-independent event is like raining and having a traffic jam. Maybe the chance of raining is 30% on any particular day, and having a traffic jam is it will be dependent on whether if it's raining, because when it's raining, there's a higher likelihood of having a traffic jam. In that sense, the two events are not independent, as traffic jams are more likely to happen when raining. Next, mutually exclusive events are events that cannot happen together. You cannot be 10-year-old and 50-year-old at the same time, right? So that's one example of a mutually exclusive event. You cannot be first and second. Okay, maybe you can, but you cannot be first and last in a race at the same time. Probably not. Maybe if there's some special rules involved, but most of the time you probably won't. Okay, and with that, we can talk about the multiplication and addition principle of probability. And so when two independent steps are carried out with A ways of being done, with the first step having A ways of being done and the second step having B ways of being done, where A and B are numbers, the total number of ways of doing the two steps are AB. Okay, so if let's say in a simple case of coin flip plus a dice roll, there are two ways of getting, or rather there are two outcomes of a coin, and there are 6 outcomes of a dice. So total there are 2 times 6 ways of 2 times 6 outcomes for rolling a dice and flipping a coin. And next, this is for independent steps. Okay, so multiplication principle is for independent steps, and addition principle is when there are two mutually exclusive methods that do the same thing. So for example, there are 3 ways to walk to school and 2 ways to take bus to school. Then there are a total of 5 ways to get to school in total. Okay, this is what addition principle is about. Because taking a bus to school and walking to school is different, right? It's mutually exclusive. Yes, so permutation is defined to be an ordered arrangement of objects. So ordered is very important because it means that the order matters in this case. To permutate n distinct objects without replacement means that, let's say we just do a simple example. We have 5 objects. We have A, B, C, D, E. To permutate them is to find out how many unique ways are there to arrange them. The first, so to find out how many ways there are to arrange them, we can think of it as we have 5 slots. We want to pick which object to put in the first slot, the second slot, the third slot, fourth slot, and fifth slot. So for the first object, because all 5 objects are still present, right now we are doing it without replacement. Okay, so first slot we have 5 choices, so we can do 5. Now there's no replacement, so by the time we reach the second slot, how many options are we left with? We only have 4 because we already used 1. And next there will be 3, next there will be 2, and finally there will be 1, because with each step of choosing which is each slot, we are taking up 1 more option. And between each of this, you are basically it's basically independent, because after you get the first one, it won't affect the rest. It won't affect the rest. You choose one regardless. No matter which one you choose, the next step only will have 4 options left, so it's not dependent, the steps. So the total number of ways to permutate will be multiplied across the different slots. So there will be a total of 5 times 4 times 3 times 2 times 1 ways. Okay? This is also notated as 5 factorial. To permutate R objects from a total group of n distinct objects without replacement, okay? So here, we are not permutating all 5 of them, we are permutating only like maybe 3 of them. So in this case, what happens? Instead of having 5 times 4 times until you get to 1, here we only times until we fill up all the slots. How many slots do we have? In this case, in the example, we have 3, right? So we have 5 times 4 times 3. Actually, here, how many objects are we trying to permutate? We're trying to permutate 3. So R equals to 3 in this simple example. And a total group of 5 objects in the simple example, without replacement, we see that we have 5 times 4 times 3. We can write it out as a factorial form by adding times 2 times 1 over 2 times 1. Why do I need to over? Because now after we divide by the 2 times 1, we get from this fraction to this. But the benefit of writing it like this is that we can write it in terms of factorial. And we notice this is equals to 5 factorial over 2 factorial. And essentially, we get this equation here. Okay? We get this equation here. So this is important because we need to know this by heart. This is how you permutate R objects from a group of n distinct objects. In essence, we can think of it as having n ways for the first object, n ways to choose the first object, n minus 1 way to choose the second object, and finally R ways to choose the last object. Continuing, we can permutate R objects from a total group of n distinct objects with replacement, and this will simply be n to the power of R. Because if we have R slots, let's say we have R slots that we want to choose from, because we are replacing the object that we chose, each of this option will just simply be n times n times n, so on and so forth. And therefore, to permutate R objects with replacement, we have n to the power of R. And finally, to permutate n objects with some identical objects. So previously, all these are all distinct. Okay, it's been written out here. It's all distinct. Okay, what if there are some objects that are identical? Okay, so let's say there are A objects of the first type, B of the second type, so on and so forth. So there are A duplicates, A number of duplicates, B number of duplicates, so on and so forth. All we need to do is actually to divide by their respective factorial. The way to think about this equation is that each time you divide by this factorial, you are eliminating the duplicates that happen. Okay? In this case, this will be a without replacement. Okay? If there's replacement, then it will be similar. It should be similar. It will be n to the power of R over A factorial, B factorial, so on and so forth. A special case of permutation is circle or cyclic permutation, where n distinct objects are placed on a circle. In this case, we basically take the first object as the reference, and this is because when you have a cyclic permutation, right, what happens is, although there are 4 ways to choose the first object, but whichever position that is being chosen doesn't matter, because now you have you can just rotate the object around. So you need to essentially ignore the first object that you pick in the case of circular permutation or cyclic permutation. So like this. Let's say we want to choose A. Let's say our first object is the first object we pick is A, okay? But if we put the A here and then B, C, D, it will be the same as picking A here and then B, C, D. And it's the same as picking the first object A, B, C, D is all the same. So because of this, because of the duplicity in the arrangements, because of how this arrangement is actually the same as all the other arrangements that is being rotated around this cycle, we have to divide by n, which is a number of slots in this case. Alright, so on the other hand, if it's a cyclic permutation, but each of the slot, each of the position or the box, whichever you call it, is already labeled, then there's already a form of reference. So then there is no more like duplicity, or there's no other, like when you put A, B, C, D like this, because each seat or each box is already labeled, there's no other way you can achieve the same kind of permutation, and therefore the number of permutation just returns back to normal, which is n factorial. Okay, so that's for permutation. It can be a little bit confusing, especially the cyclic permutation, but just remember that same permutation are not counted twice in the number of permutations. So therefore, we have to eliminate any similar permutations if we are just looking at number of permutations available. So for combination is used for choosing a set of objects from a larger group. In this case, order does not matter. So I'm sure you have heard of things like combination logs in school, where you need to rotate this thing, and then there's a log. You rotate to one number, second number, and third number. Sometimes it's called combination log, this thing, the log. But actually, if you think about it, because the order matters, right? So it's actually not a combination log, but it's actually supposed to be called a permutation log. But yeah, anyways, just one of the many things that doesn't make sense in our day-to-day language. Yeah. So anyways, combination is when order does not matter. Here, the problem don't usually deal with identical objects, and we will need to usually choose like objects from a group of a larger group of objects. And here, you should try and remember this. This is also notated as n choose r, or bracket nr. It's like how many ways can you pick out, let's say, two objects from. Okay, let's just do a simple way. Let's say we have three objects, A, B, C. Okay, what exactly is choosing? Choosing is we want to see how many ways we can choose the objects out, right? So if we want to choose one object, then there are three ways, because we can choose A, B, or C. Okay, three ways. If we want to choose 0 ways, how many ways are there to choose 0 objects? Sorry, how many ways are there to choose 0 objects from this 3 object? Then it's only one way, right? Because then you choose nothing. You may think the answer is 0, but no. To choose 0 objects, there's one way, which is choosing nothing. Choosing nothing is one of the possible ways. Okay? Sounds a little counterintuitive, but don't be scared. It is a way. Next, we can try and choose 2 objects from 3 objects. Okay? Choosing 2 objects out of 3 objects is actually the same as choosing 1 object to leave out. So it will be natural as to know that choosing 1 object is equals to choosing 2 objects. Okay? And this will be equals to 3 ways. You can choose AB, AC, BC. That's 3 ways. It's the same as choosing which one to leave out. And of course, choosing 3 objects there's only one way of choosing 3 objects, which is to choose all 3. And this is the exact opposite of choosing 0 objects, because choosing 0 objects is like opposite of choosing all 3, right? It's like choosing none. Okay? So this is what choosing is about. It's possible for you to list out all the different ways to arrange to choose your objects, like what I've done. Like ABC, you can, between ABC, you want to choose 2, you can choose AB, AC, BC. Okay? It gets extremely difficult when you have many different letters. So let's say there are 5 objects, A, B, C, D, E. You want to find out how many ways you can choose, let's say 3 objects, right? Then 5 choose 3. And that is when things start to get more complicated. And you should use the formula here, where you have 5 factorial over 2 factorial times 3 factorial. And this means 5 factorial is 5 times 4 times 3 all the way, right? 3 factorial is 3 times all the way, right? So it's actually just 5 times 4. We can cancel out the 3 factorial within the 5 factorial over 2 factorial. 2 factorial is 2, so this gives us 10. So when numbers get large, just use the formula. Okay, try and remember it. If you can't remember it, calculator helps you. You can use the calculator to help you. Actually, for stats and all this, there's a lot of parts where you need to use calculator. So familiarize yourself with the calculator. It's super important. When solving questions involving P and C, right, first step, you must determine if the order matter, because this will tell you whether if you want to use the methods involved for permutation versus combination. Second step, consider whether if there are any non-distinct objects. So non-distinct objects are usually in the case of permutation, because when it comes to combination, it can get quite difficult to factor in. Okay, notice that we didn't really talk about that. Yeah, okay. So then finally, consider if there are replacement. Again, this is usually for permutation also. Combination is possible, but then that's not really the point, right? The point is you want to choose from a group of objects. If you keep adding it, then it's no longer the same group. All right, so of course, it's still possible to choose. That one is just draw a tree diagram. Okay, just draw a tree diagram. Say what's the first choice, second choice, third choice. All right, next, probability. Probability is essentially how likely something happens by chance. The probability of rain is an example of a probability. If it's not going to happen, it will be 0. So what's the probability of there having rain on Mars? It's okay. That's actually not impossible, but let's say something like probability of rain on the moon. We know the moon does not have an atmosphere, so it will be 0. It's basically impossible. Okay. Next, then from impossible you have not likely. Not likely is usually defined to be 0 to 0.5 in terms of probability. One thing to take note, right, is that number one, all this scale, right, is not super official. Like it's not like everyone in the world knows what exactly not likely mean, right? But one thing that you should walk away with, one knowledge you should walk away with from this one point is that the decimal 0.5 is equal to half and equal to 50% when it comes to probability. These three are equivalent. I mean, normally 0.5 and half is equivalent in all cases of math, but like sometimes it's not immediately obvious that 0.5 and 50% is the same thing. Next is equal probability of happening or not. That is just 0.5. And likely is more than 0.5. And certain is 1. Of course, here in the case of fraction and decimal, it's just 1. Okay. Probability can be numerically represented using decimal fraction percentages and even graphically using Venn diagram. So Px represents the chance or probability of event X happening. This is a notation, take note of it, and Px is not just, sometimes it's written like this, so X equals to X. So in this case, you can read it as this is the random variable that we are thinking of. For example, this capital X, this is a capital X, this is a small x. So this capital X can be the dice roll. Then this small x is whichever particular number, maybe 3 or 4 or 6 or whatever. Okay? So the probability of the random dice roll being equal to 3 or 4 or 6 or whichever number, then you can write down the probability for that occurrence. So yeah, probability is usually represented with like a capital P with a bracket. Okay? Whereas relative frequency is a closely related concept compared to probability. Rather than telling you what's the likelihood of it happening, it is the frequency of the outcome against the total number of time tested. Okay? So it's the frequency relative to the total number of times. Essentially, it's basically probability. But here is about events actually happening. Probability may be just an estimate. Like, judging by the clouds, I think it's likely to rain later. There's a probability. Relative frequency is like, based on past data, in the month of May, the chance of raining is 50%. So it's very similar. You sometimes can be used interchangeably. So don't worry too much. Next, we have complementary events or complement events. These outcomes are not the same as the event. So what complement mean is just the opposite of what happened. So rain versus not rain. Raining is the complement event of not raining. So on and so forth. Getting heads is the complement event of getting tails. So the complement and complementary event, they would add up to 1 if the event is definitely gonna happen. So like, it's either a rain or not rain, right? You can't have like, what exactly does it mean to be in between? Like drizzle is considered raining. So in that case, the chance of the day happening is 1, but the probability of the rain and not rain will add up to 1. Unless the day doesn't happen somehow, if Earth get destroyed. Yeah. Okay, anyways. Using PNC, it's possible to compute the total number of outcomes. This can then be used to find the probability of some events. And of course, this assumes that the outcome is the probability of outcome, each outcome is the same. So in the case of like the dice roll, chance of each outcome is the same. So we can use PNC, we can find out the total number of outcome, then we can say what's the chance of some event happening. So one example would be what's the probability of heads and the even number. Heads and the even number. How many ways can we form heads and even number? We know that there are 3 ways, right? Because it's heads plus 2, heads plus 4, heads plus 6. How many ways are there to get the outcome this way? Then it'll be 2 times 6, right? Which is total of 12. And then we can see there's 3 out of 12. The chance of us getting heads plus even number is 3 out of 12. Of course, this is not exactly permutation or combination, but it's basic like counting. Okay? I mean, PNC are counting, so it's counted. Okay? So anyways, moving on to addition rules of probability, we can see that probability of A or B is equals to the probability of A union B, and this is equals to probability of A plus probability of B and probability of A intersect B. So for this, it might be easier to just see a Venn diagram. So let's say we have a Venn diagram here. Okay, so this is event A happening, this is event B happening, and the chance of event A or B happening will be this complete shaded area. Okay, assuming they are independent, okay, that will be later. Independent and stuff will be like around this section. Okay, so in any case, we can see that this is equals to PA, which is this area, plus PB, which is this area. But notice that we double counted the middle. So this is equals to, so we need to subtract the middle, which is P, A intersect B. So P probability of A and B happening at the same time. So this is true for general case, okay? This is true for general case. There are some more specific case, which I almost went into just now, but we'll go into there in time. So this additional rule of probability is important because sometimes you do not know directly whether how A and B are related. But this rule will always hold true. Other method of calculating may not necessarily be true, so you need to be careful. So in other words, this means that either event A or B happening is the same as chance of event A happening plus event B happening minus the chance of event A and B happening at the same time, as double counted. Yeah, this is basically all. If event A and B are mutually exclusive, there's no chance of them happening at the same time, and therefore the probability of A or B happening is just addition. Okay, so this actually goes back to how we were trying to explain the mutually exclusive event, which is this clause over here. Okay, it goes back to this point, and yeah, it's basically a more mathematical way of showing that. Next, we have conditional probability. So given that probability A happened, the probability B is notated like this. So it's pronounced as, is said as probability of B given A. So we already know that A happened. then what's the chance of happening B in that situation? In this case, the mathematical way to write it is here. Probability of B given A is written by probability of A intersect with B divided by probability A. What this means is we take probability A as the whole probability space now. So we know that probability A already happened. We have to take that as the unit, or take that as okay, before probability A happened, we do not know, like, okay, there could be probability A, there could be event A happening, event B happening. But now we know that event A already happened, so we have to divide the probability of A and B happening with probability of A, because we know probability A already happened, is already a certainty. That's why this equation come about. And now you can see that so think of it as A happening. After A happened, the total possible outcome now shrinks to only within A. Okay? To draw a Venn diagram, we can see that now that we know A have already happened, so this is now the new sample space. This is now the new total probability space. The chance of B happening is simply this. So yeah, try and see if you can draw the same Venn diagram and see if you can visualize this. Next, we have dependent events. Dependent event is when one event affects the probability of another. So going back to the same example of traffic jam. When there is rain, there's a higher likelihood of traffic jam. So the conditional probability is different from the individual probability. And the conditional probability is what we just talked about when probability of B given A. So if probability of B given A is not equals to probability of B happening on its own, that means A and B are dependent. That's all. So if they are asking you to show whether if they are dependent or not, this is the line that you're looking for. Okay? This is quite important. If they're asking you to show whether if two events are dependent or independent, you use this line to show. And yeah, if they are equal, then they are independent. If they are not equal, then they are dependent. Quite simple, this part. Finally, we move on to the multiplication rule of probability, which is also what we talked about very early on. Previously, okay, one thing to note is that why do we talk about it twice? Because previously is a general multiplication rule of like number of ways of counting, whereas here is just a rule of multiplication and addition rule of probability. So they're slightly different, but intuitively they are almost the same. So yeah, for multiplication rule of probability, we see that probability of A and B must be equals to their intersection, and this is equals to probability of A given a probability of A multiplied by probability of B given A. So here is A happened, then after A happened, B happened. Or probability of B, which is probability of B happening, then multiplied by probability of A happening after B happened. Okay? Take a moment, this might be a bit confusing. Take a moment to think about why this is the notation. Very important to understand. Okay? And this is the basically inwards description of inwards. First A or B happened, then we consider probability of the other event happening, given that the first happened. Okay. If A and B are independent, that means they do not affect each other's probability. We see that this will be equals to this. It's a condition that is given here, over here. Then, and this is also true. So probability of A and B equals to probability of A and B happening. Now, this is why we notice that when we say things like coin flip and dice roll, we can just multiply the probability up. We can just multiply, we want head and 5. So heads and 5 is, what's the chance of heads? Is half. What's the chance of 5? Is 1/6. So you just multiply. If they are not dependent, if they are dependent, then we cannot just do this simple multiplication, and we will need to do more complicated maths. And in that case, the best way to do it is by doing a probability tree. So when you have like dependent probability, the best way is to draw a probability tree, especially when you have like multiple steps. So one example of a dependent probability is described here. So we are taking out multiple marbles from a bag with red and blue marble without replacement. So note that each step, the probability of red and blue will change on the situation. This means the probability are dependent. So probability of each branch is the probability of each outcome branch. For example, let's say I want a red and then red. This would be the product of all the probability in that branch. So let's say the first branch is 3 out of 10. The second branch will be 2 out of 10. Why is it 2 out of 10? 2 out of 9. Why is it 2 out of 9? Because now the marbles reduced in number. And the number of red marbles also reduced in number. So therefore the chance is 5 out of 90. And then if you want red and blue, then it will be 3 out of 10 first. Then here there will be 7 out of 9. So it will be 21 out of 90. Okay? So on and so forth. So the chance of each branch will be the probability of each of the probability multiplied down the branch. The total probability here should add up to 1 because this series of events definitely happened. It's just that we do not know the outcome. If this series of events does not add up to 1, that means there's a chance that all these things didn't even happen in the first place, which defeats the point of the question, right? So one thing to note is that, right, although I said just now that there's a replacement, this is done without replacement, right? But actually the probability tree diagram would work regardless of whether if there's replacement or not. If there is replacement, then all we need to do is then change this to, instead of 9, we change this to 10 and this is 3, right? Because now you took out a red marble, you replace it, it's still, that means the probability of the red marble is still 3 out of 10. Okay? So in this case, just write out the probability for each step that you take and just calculate the branch probability one by one. It should give you a correct answer if you do it carefully. Okay? And with that, we basically summed up the permutation, combination, and some of the basic probabilities. I hope this video helped you, and happy studying!